All right, let's talk about one of the most critical things you'll ever have to deal with in patient care: arterial blood gases. And listen, this isn't just about memorizing some numbers on a lab report. No way. Understanding this delicate chemical balance, it is literally the key to saving a life. So let's get right into it.
So here's what we're going to do today. Think of this as our game plan. First, we'll cover the absolute basics, that critical balancing act in the blood. Then, we'll meet the body's first responders, who's doing the work. After that, we're going to crack the ABG code itself. And then, the fun part. We'll apply all of it to a case study, a real-world scenario. We'll wrap up with your must-do, priority actions at the bedside, and a super quick recap to lock it all in.
And I'm not kidding when I say this, the stakes are so high. When a patient's pH strays just a little too far from that super narrow normal range, the body's entire system starts to fall apart. Proteins literally break down, essential metabolic processes just stop. And without you stepping in and stepping in fast, the outcome is fatal. This is exactly why we've got to nail this down.
Okay, so let's get into the nitty-gritty. We're talking about a critical balancing act here, right? We're diving into the chemistry of the blood. It all comes down to one core measurement. So what is pH really? Why does this one little thing have so much power over everything?
It's actually pretty straightforward. The pH scale is all about one thing: hydrogen ions. That's the H in pH. So think of it like this. The more hydrogen ions you have floating around, the more acidic your blood is, and the lower the pH number goes. Make sense, right? And if you have fewer hydrogen ions, well, your blood becomes more alkaline or basic, and the pH number goes up. The body's job is to keep this teeter-totter in a perfect, delicate balance, 24/7.
So who are the MVPs here? Who's in charge of keeping this balance? Well, it's this amazing tag team, the body's first responders. We're talking about the lungs and the kidneys. These two are constantly working together to fix any little shift that happens.
Okay, this is so important to get. The biggest difference between these two is speed. Think of the lungs as the sprinters, the fast first responders. If the blood gets too acidic, bam, within minutes they can start breathing faster to blow off CO2. And remember, CO2 is an acid, so that's a quick fix. Now the kidneys, they're the marathon runners. They're the slow, steady, and incredibly powerful backup. It might take them hours or even days to really get going, but they make these super precise long-term adjustments, deciding exactly how much hydrogen or bicarbonate to hold onto or get rid of. Fast and furious versus slow and powerful. That's the game.
All right, so now we know who the players are. Let's start cracking the ABG code. This is where you become a detective at the bedside. Before you can figure out what's wrong and what to do, you have to know what normal looks like. So step one is always knowing the numbers cold. Okay, grab a pen or just burn these into your brain because these are the core numbers. Normal pH, super tight range, 735 to 745. PaCO2, that's our respiratory value. It hangs out between 35 and 45. And then HCO3 or bicarb, that's our metabolic, our kidney value. That should be between 22 and 26. That's it. 735 to 745, 35 to 45, and 22 to 26. These are your guideposts. Everything starts here.
Okay, so you've got the normal values. But what happens when they're not normal? How do you figure it out fast? Well, there's a trick, a super simple mnemonic called ROME. And it stands for respiratory opposite, metabolic equal. I'm telling you, this little thing is a powerhouse for figuring out what's going on in seconds. Let's break that down. Look at the chart for anything respiratory. The pH and the PaCO2 are going to move in opposite directions. See that? Respiratory acidosis. pH is low, but the PaCO2 is high. They're going in opposite ways. Now, for anything metabolic, the pH and the bicarb are going to be equal. They move in the same direction. So for metabolic acidosis, both the pH and the bicarb are low. See? Respiratory opposite, metabolic equal. It works every time.
Okay, theory is great, but let's see it in action. Time for our case study. We're going to map this out step by step, just like I'm drawing it on a whiteboard for you. Let's follow the breadcrumbs and see how this plays out in a real patient with respiratory acidosis.
So where does it all begin? The cause, the etiology. In this case, it's an opioid overdose. This is a classic textbook trigger for what's about to happen.
So what does that overdose actually do? Well, the opioids hit the brakes on the central nervous system. They go right to the brainstem and shut down the drive to breathe. So what do you see at the bedside? You're going to see your patient's breathing get super slow and super shallow. That is hypoventilation.
And what's the next domino to fall? Well, if you're not breathing effectively, you can't get rid of that carbon dioxide. And we already know CO2 is an acid, right? So it just starts building up and building up and building up in the blood. The logic is simple. Less air out means more acid in. We call that state hypercapnia.
And here's the result. All that extra acid, all that CO2, starts to overwhelm the body's natural defenses. The pH just can't handle it anymore, and it plummets, dropping way below that 7.35 mark. And boom, your patient is officially in acute respiratory acidosis. Now, this change in chemistry is absolutely devastating to the brain. As that CO2 level creeps up, you're going to see a really fast neurological decline. Your patient might get confused, delirious, even paranoid, and it can spiral so quickly into seizures and then a coma. These are your high-yield exam triggers, your major red flags at the bedside. You have to recognize this. Okay, you've spotted the signs, you know the pathophysiology, you know the why. The big question is, what are you going to do about it? Right now, what are your absolute priority actions at the bedside to pull this patient back from the brink? There's a magic number here, and it's a scary one, a pH below 7.1. That is your red flag for severe, life-threatening acidosis. At that point, the patient is at huge risk for total circulatory collapse. So when you see a pH that low, you need to be one step ahead. You should be anticipating an order for IV sodium bicarb to help fight back against all that acid. Let's be crystal clear. Acute respiratory acidosis is an airway and breathing emergency. Full stop. So your priority actions follow that. Number 1, assess your ABCs: airway, breathing, circulation. Number 2, get help. Don't be a hero, call a rapid response. Number 3, treat the cause. In our case, that means reversing the overdose with naloxone. And finally, you have to be ready to support their breathing. That could mean getting a BiPAP machine ready or preparing for intubation so we can take over and blow off that toxic CO2 for them. All right, let's put it all together. Time for the 30-second patho recap. We're going to run through the whole flow one more time super fast to really lock it in your brain. Ready? Here we go. It starts with the opioid overdose. That leads directly to hyperventilation, slow, shallow breathing. That hyperventilation causes CO2 retention, which we call hypercapnia. That hypercapnia causes the pH to drop, which is acidosis. That acidosis leads to the neurological decline, the confusion, the seizures. And that decline is your cue for the priority ABC intervention that stops this whole deadly cascade in its tracks. So it all comes down to this. You're at the bedside. Alarms are going off. You see the numbers on the monitor. You understand the pathophysiology. You understand the why behind every single change. The only question is, what's your first move?